So far in Chapter 17, we've talked almost principally about additional aspects of equilibria that are in solution. And mostly they've had to do with acid and base substances, acid-base titrations, and common ions that have to do with acid and bases. Now we shift gears in these last couple videos to a different type of equilibria called solubility equilibria, where a tiny bit can make a difference. So these reactions are what are called heterogeneous reactions because they involve a solid and things that only dissolve just a little bit. This dissolution, in other words dissolving, and precipitation occur both within us and all around us. Tooth enamel dissolves in acidic solutions, for example, causing tooth decay, and the precipitation of certain salts in our kidneys produces kidney stones. The waters of earth contain salts dissolved in water, and as water passes over and through the ground, we have different dissolvings going on. That's how we get calcium or magnesium or carbonate or iron into our water, making hard water. Coral reefs are principally made of calcium carbonate, as we saw at the beginning of the chapter, and precipitation of CaCO3 from groundwater is responsible for the formation of stalactites and stalagmites within limestone caves. And that's what this solubility equilibria is all about, and we'll put some mathematics to it, and we'll make it so we can understand when things form solids and when things can be dissolved, even though slightly dissolved. But that tiny part can make a difference. So the solubility of substances dissolved in water is given by an equilibrium. Here's an example. Barium sulfate is usually a solid, and it's usually insoluble. And if you look at your periodic table, remember we had a solubility table right here, and then some of them, like for example strontium sulfate, silver sulfate, barium sulfate is on here too somewhere. Those are slightly soluble, it says marked with an asterisk. And those slightly soluble ones, even ones that are mainly water insoluble right here, usually end up in equilibria like this because just a little bit of them will dissolve, and that little bit can make a big difference. Just think about lead or mercury. Those are poisons that even if you just get a little bit, they can make a big difference. These concentrations of these ions give us the solubility. Solubility is measured in molarity or in concentration. The equilibrium constant of these types of reactions at 25 degrees Celsius for many of these solubilities is recorded in Appendix D. So if you look at the back of Appendix D right here, you can see that these solubility product constants, which is the K for a reaction such as this, are listed for many different substances right here. And if you look at their numbers, you can see that the numbers are exceedingly small. 1 times 10 to the negative 14th, 1 times 10 to the negative 28th, 1 times 10 to the negative 10th. Really small numbers because not a lot dissolves, but what does dissolve can make a big difference. So these solubilities are recorded in Appendix D, and when we write the K for them, that K is called the solubility product equilibrium constant, and it's symbolized by K with a little SP down below it, and we just call it KSP for solubility products. Remember, no solids can go in an equilibrium constant expression, so that's why I just did products and then divided by 1 because the reactant is a solid. Since this is the product of the dissolved species, the K is called the solubility product. Product meaning multiplied together right here. And so KSP for barium sulfate is 1.1 times 10 to the negative 10th. And you could look that one up here in Appendix D. And for some of your problems, you'll need to look them up there. It's small, so that means it's not very soluble. But we're still interested in that because, as we said, certain things that are just a little bit soluble make a big difference. So here's some words in this portion of the chapter that become really confusing. First of all, the word solubility versus the word molar solubility versus the word solubility product, or KSP. Well, what's the difference? What's the similarities? Well, first of all, solubility is usually measured in grams per liter. Grams per liter. How many grams dissolve per liter of solution? Molar solubility, on the other hand, is molarity, or the moles that dissolve per liter. And these brackets right here represent the molar solubility of the barium ion from barium sulfate. The solubility product is the multiplication of the products' molarities raised to the power of their coefficients. And so it's the equilibrium constant of the dissolving process for whatever species it is. Solubility calculations indicate the maximum of solute at a saturated solution, right at the point of saturation when no more could be dissolved. So here's one example problem remaining in this video. This is sample exercise 17.10, and it simply says, take the fairly insoluble salt calcium fluoride, and please write the equation for dissolving, the equilibrium equation, and then second of all, write the KSP expression, or the KSP equation. So first, take calcium fluoride, solid, put a double arrow, and then split it up into its ions. And we're going to get calcium, and then we're going to get 2 fluoride ions. This is the equation for the dissolving of calcium fluoride. Now let's write the KSP, or the equilibrium constant expression, which would be products raised to the power of the coefficients divided by, well, 1, because there's only a solid here. So the solubility product would be the multiplication of the concentration of calcium that dissolves, the molar solubility, and the molar solubility of fluoride ion raised to the second power, because there's a 2 right there. In the next video cast, we'll give a number of numerical problem solvings for these solubility products, molar solubilities, and solubilities in grams per liter.